So we left off with question number 8, okay, where we were saying if I had 1 cubic centimeter of lead and 1 cubic centimeter of carbon, assuming that in that cubic centimeter I had the same number of atoms of lead and the same number of atoms of carbon, why is the lead so much heavier?
Because the lead has many more protons and neutrons.
Exactly. Lead atoms are quite simply bigger. Okay? If I'm looking at a carbon atom, okay, a carbon atom has, well, 6 protons and 6 neutrons, so it's not very big, it's not very heavy. By comparison, a lead atom has 82 protons and 125 neutrons, it's big. Okay? Just the atoms are simply, there's more there. So if I have the same number of atoms of each, obviously the lead is going to be much heavier. Okay? Everybody all right with that? Just goes back to that idea that the atoms of the same element are the same, atoms of different elements are different. It goes back to that point of the atomic theory. Okay, number 9. Nuclear reactors use atoms with very large nuclei like uranium, which has 237 particles in its nucleus, for fission, which is the splitting of the atom. Okay, why wouldn't they use smaller, less dangerous atoms like lithium, which only has 7 particles in its nucleus? So, why?
Because it's much easier to split a particle with 237 neutrons or protons than only 7.
Yeah, first part, way bigger target, definitely. Okay, if it's bigger, it probably holds more what? Energy. Probably holds more energy. Okay, and also on top of that, the bigger an atom gets, the less stable it generally becomes. Okay, those forces that hold it together get weaker with distance, actually weaker exponentially with distance. So as an atom gets larger, they become more and more unstable. And I think we talked about this, but hey, if you look at a lot of these newer or more newly discovered elements here, okay, we don't have really accurate numbers for their atomic masses because they don't last very long. Okay, they're essentially made in a particle collider, okay, like the Large Hadron Collider. They don't last but for a fraction of a second, and the best reading you can get is about this close. Okay, we don't know a lot about them because they're just that unstable. Okay, everyone all right with that idea? So, yeah, kind of all of those things. Bigger target, bigger means more energy. Okay, bigger means less stable, more easily broken. Okay, and then number 10, atoms are indivisible. Why was this statement believed for so long, and why is it still somewhat true, provided there's no human technology present?
Well, it was believed that atoms were indivisible for so long because for a very long time they didn't really have any technology to split them.
Exactly, yeah. There wasn't a way to split them, right? They're too small. We don't have an instrument that can cut, okay, an atom. Even a laser, okay, is not going to be able to like cut an atom, right? It's just, they're just that small, okay? We didn't have anything that was capable of doing it until we discovered how to, build something that would shoot even smaller subatomic particles at the atoms in order to make them break, okay? And why is it still somewhat true? Well, because atoms are generally, at least most elements are generally stable, and they're not just going to fall apart. Okay, again, the bigger elements that are less stable do that. That's why some things are radioactive. Okay, some things are radioactive because they're so big that their atoms are unstable, and the neutrons just come off. Okay, and they emit radiation when that happens. Okay, and of course there were a number of very talented but unfortunately very short-lived scientists who studied that. People like Marie Curie, okay, Henri Becquerel. Okay, they were scientists who discovered the nature of kind of radiation. They just didn't realize that it was killing them while they studied it. Okay, like did I tell you guys this about Henri Becquerel's desk? Okay, so Henri Becquerel studied, basically fluorescent radioactive materials, and he kept them in his desk. And so he was like always sick. Like he was a very sickly person because he was always getting radiation poisoning. To this day, his desk is in a museum behind lead glass because if you took a Geiger counter, those things that go tick, tick, tick when you get them near radiation, if you put that near his desk, it goes crazy. His desk is still radioactively hot because of all the crap he had in it, okay, that he was studying his special rocks, okay, that he was studying that were unfortunately slowly killing him. Mary Curie, same thing, okay. They didn't understand because there was no way to detect that stuff. It was coming off, but it's invisible, okay. You just feel sick. Like when you get an X-ray, like, you know, feel the radiation going through your teeth when the dentist takes an X-ray of your face, okay? Or if you break your arm, you don't feel the X-rays, but they're going through you, and it was the same thing for them, okay? These things were unstable, they were emitting radiation, and we didn't know the effect that had at the time. Okay, okay, so from what you know of the structure of the atom, why do you think it stays intact? Why do the electrons not fly off or the protons separate from the nucleus? Probably the electron part is the easiest. Okay? Why do the electrons orbit the nucleus?
The protons are in the nucleus, so they're attracted to that.
Exactly. The nucleus is positive, the electrons are negative, opposites attract, they orbit each other just like the sun is, or the Earth is attracted to the sun, and the sun is also attracted to the Earth. Okay, so it's like that. Now for the protons in the nucleus, that's a little more complex. Okay? You would think that because there's, you know, electrons out here, the protons would want to move towards them. But protons are exponentially heavier than electrons are. Electrons are tiny, they're almost massless. Okay? The mass of an electron is, as it here, let me see if I get it right, 9.11 times 10 to the minus 31 kilograms. Okay? So that's 911 with 30 zeros and then the decimal. Okay, so it's crazy small, right? I can't remember the mass of a proton, but it's like something like 10 to the minus 18 or something. It's considerably bigger, okay, in mass. So the protons are more likely to stay together in the nucleus because there's also neutrons in there, and the neutrons are the same size. Okay, so there's going to be these kind of interatomic forces that are just going to hold that part together. By comparison, if I have something that's purely positive right here and something that's neutral right here, well, neutral almost seems negative when you compare it to something that's completely positive. Okay, so there's going to be some attraction between those things that keeps them together, all in the nucleus there. Okay. All right, and we talked about number 12 already a little bit, okay, the glow-in-the-dark stuff to do with the electrons jumping from one energy level to another, okay? So if we had those glow-in-the-dark materials outside, they absorb energy from the sun, they gain energy, they move too fast for the orbital that they're in, so they make what we call a quantum leap. They jump from one energy level to another one, okay? And they might do that a couple of times. And then when you remove them, and put them in the dark, remove them from that source of energy, they begin to fall because now there's no energy to hold them there. They can't maintain that position, and as they fall back down, they release the energy that they had gained. For a glow-in-the-dark material, it's released as light, and the material glows. Okay? If we're talking about plants, okay, that's released in a way that allows certain molecules to gain phosphate groups and things like that, and give it energy to carry out photosynthesis. So as those electrons in the chlorophyll fall back down, the energy gets used to break up carbon dioxide, break up water, and put them back together as glucose. Okay, that's where that energy comes from. It comes from the energy of falling electrons. Okay, that's how de Broglie's model explains it. All right, any other questions on those? Okay, so I wasn't, looking for like super detailed answers, just kind of general things, cover it, kind of put it in your own words so that you have it. Okay? All right, let's move on to lesson 2, naming compounds here. Okay? So what we go over today is probably all going to be very familiar to you. We probably won't get into any new stuff that you haven't done on naming compounds. Okay, but it'll be a good review before next week. I gotta give you guys your periodic tables. So, first thing we need to talk about are the 2 types of compounds that we're generally going to deal with in Science 10. Okay, and that would be ionic compounds and molecular compounds. How are they different? Pietro?
Ionic is composed of a metal and non-metal, and, sorry, what was the other one?
Molecular.
Molecular is made up of two non-metals.
Exactly. Okay, so if I've got an ionic compound, then the ionic compound is going to contain something from the left side, that's the metals, okay, and something from the right side, okay, that would be the nonmetals. Remember that this dark black line here is called the staircase, okay, and it does separate nonmetals on the right from metals on the left. So an ionic compound will have one of each, whereas molecular compounds are going to be made up of two or more nonmetals. Okay. So as long as we can do that and know what kind of compound we're looking at, that's important. And then obviously be able to write the proper formulae. That's formulas plural because you don't actually say formulas. It's formulae when it's plural. Okay. And proper names, okay, for those chemical compounds. All right. So you guys have probably done that before, and you'll probably be pretty comfortable with this as we go along. Okay, so as we said just a minute ago, ionic compounds occur when you have a metal and a non-metal bonding. Now, ionic bonds, or the bonds that cause ionic compounds, are very different from the kind of bonds that cause molecular compounds to form. Okay, and the reason is the way the electrons act. Okay, electrons are a very important part of compounds forming. In ionic compounds, you will have a metal that wants to give away electrons, bonding with a nonmetal that wants to gain or take electrons. Right? The reason that some things, some atoms or some elements want to give away electrons and some want to take them is about having a certain number of shells or orbitals filled. Okay? So if we're looking at almost like a Bohr diagram of, let's say, this situation here with sodium and chlorine. Okay, sodium okay, so sodium, if I'm looking at sodium, what's the atomic number for sodium? 11. Okay, so that means it has 11 protons, it has 11 electrons, and it's 22.99, so it's got 12 neutrons. Okay, so what we do is we kind of draw a Bohr diagram here of sodium. So sodium's first orbital can hold 2 electrons, like so. Okay, and its second shell can hold 8. We generally draw them like this, even though that's maybe not really how they go. Okay, that's how many electrons now? 10. But sodium has 11. Okay, now for whatever reason, atoms want to have a full outer shell of electrons. Okay, they want to be like their nearest noble gas and have their outer shell be full. So for sodium, that means either finding 7 more electrons to fill that outer shell, or finding somebody who wants to take 1 off of its hands. Sort of make sense? Okay, is it way easier to find somebody to take 1 off your hands and find 7 more? Mm-hmm. Probably. Okay, now, if you're looking at chlorine, chlorine's in the exact opposite situation. Okay, so with chlorine, okay, we got 2 in the first shell, okay, we've got 8 in the next shell, okay, for 10, and then we've got 7 in the next shell. That shell can hold 8. How many more does it need?
1.
1. You see why these two get along so well? Okay, they both have what the other wants. Okay, the ability to fill their outer shell. For sodium, the ability to fill the outer shell is to get rid of the outer shell and have the lower shell become the outer shell and be full. Okay? For chlorine, it's to pick up 1 more and just simply fill the empty space. Okay? So these two things will get along very well. And sodium will give away its electron to chlorine. Now, if sodium gives away that electron, then yes, its outer shell is now full. But it now has 11 protons and 10 electrons. So it now has a charge. Would you agree? They're no longer balanced. Now sodium has a charge of +1 and is an ion. Right? Once an element loses or changes its charge by either gaining or losing electrons, okay, it becomes an ion. So now we have a positively charged sodium ion. The same is true for chlorine, except instead of being positively charged, it's now negatively charged. It has a charge of -1. Okay? So these two elements have formed an ionic bond with each other by trading electrons. Okay? Now, in any kind of bond, can you trade protons and neutrons?
No.
No, you can't change the nucleus. Remember, if you change the nucleus, you change the stuff fundamentally. But you can give away and gain and lose electrons constantly. It doesn't change anything other than your charge. Right? So these two things are now bonded together because they've traded these electrons. Ionic bonds are very weak. Okay, very weak. Because this is going to sound terrible, but they both got what they wanted. Okay, their outer shells are full. Okay, they don't have any reason to stay together anymore. They got what they wanted. Don't take that from a sociological point of view, but okay, chemically speaking, okay, it's kind of like James Bond, kind of like that. Okay, like ionic bond, taken not shared. Okay, we're just taking that electron away. So you can break ionic bonds very easily. The two things will be happy. They'll keep the electron that they gained or be happy to have lost it, okay, and just go about being charged. Okay? So the bonds are quite weak. Molecular bonds, on the other hand, are incredibly strong because instead of trading electrons, the two nonmetals have to share it. Okay? So they can't leave each other or they'll be unfulfilled. Okay? Because they have to share 1 or 2 or even sometimes 3 electrons. Okay? And it's the only way they can be happy is if they're there and stuck to that other thing and sharing those electrons. Whereas here it's like, here, have it, I don't want it anymore. Okay? Now go. Okay? You got what you wanted. Okay? So very different kinds of bonds.
So then wouldn't this ionic compound, there's 2 atoms that are no longer, that are not together.
Right.
So, like, this is the compound for table salt.
Yep.
But how does that work if they're 2 separate?
Well, when it's a crystal,
Atoms.
when it's salt, like you would put on your food, it's together.
Yeah.
Dissolve it in water, and they go apart. Okay? That's why if you dissolve salt in water, the salt water will conduct electricity. If you dissolve sugar in water, which is molecular, it won't. It needs the charged particles, these ions that are positive and negative, to be able to conduct the charge.
So would that happen every time, or like in that crystal form, would it just?
They would be together in the crystal form, and if it's dissolved, then it would be separated. And they'll react quite readily with things because they're ready to split. Yeah, they're ready to come apart. That sort of making sense? Okay. All right, so that's ionic bonds. Basically what you need to know about the ionic bond is weak, involves gaining and losing electrons, results in charged particles. Okay? Those 3 things are kind of the nature of ionic compounds. We'll talk more about their properties next week, but that's generally what you need to know about ionic compounds. Okay, if I put those 2 things together, I get that compound. Would you agree?
Yeah.
What's the name of that?
Salt.
Okay, what's the actual chemical name of that? Sodium chloride. Okay, here's the thing with using the word salt. Okay, I mean we specified table salt, but a salt is technically any ionic compound. Because all ionic compounds are crystalline solids at room temperature. They all look a little bit different. Okay? They may have different colors, they may have different crystal shapes, but technically any ionic compound is referred to as a salt. Okay, like we have the kind of salt you use to melt ice in the wintertime. Okay? It's usually like calcium chloride and a few other things. Okay, that's a salt. Okay, so salts are any ionic compound. We always want to give the technical name for things. The only exception is water. Okay, if you see H2O, you can just call it water. You don't have to go with like dihydrogen monoxide or hydrogen hydroxide or whatever, just water. Okay, so this stuff would be sodium chloride. Okay, did I have to do anything special to name that?
No.
No, I just had to look up the two parts. Hey, boss.
Sorry to interrupt. Can I please have lilac green?
You may.
Thank you.
You're welcome. All right, so all I did then was I found the name of the metal, I found the name of the non-metal. Did I change any of their names?
No.
Yes.
I did. What did I do to chlorine?
Well, you
Added I.
changed the, like, end with I.
Right, I changed the ending of the non-metal to "ide." Okay, and that's true in pretty much all compounds, molecular and ionic. The second thing is always going to have its ending changed to "ide." Okay, if it's just binary. We'll talk about a few exceptions involving these things up here in the table of polyatomic ions in a bit. Okay, but we generally go name the metal, unchanged, name the non-metal, change its ending to "ide," and you're good. Okay, naming ionic compounds is pretty straightforward. Do I ever need prefixes?
Yes, sometimes. It's situational.
Okay, in an ionic compound, do I need them? No, I only need them in molecular compounds. Okay, and here's why I don't need prefixes in an ionic compound. Ionic compounds can only go together one way. Okay, if I put sodium and chlorine together, it's always going to be 1 to 1 because this is a +1 and this is a -1. If I put calcium and fluorine together, okay, it's always going to be this because calcium is +2 and fluorine is always -1. Okay, there's only one way for them to go together, so I don't have to say it's difluoride. There would always be 2 fluorines when fluorine is with calcium, so that would simply be calcium fluoride. Okay, now when I'm talking about molecular compounds, because they're not trying to balance charges and they're sharing electrons, there could be any number of configurations for, say, nitrogen and hydrogen to go together. Okay, or like nitrogen and oxygen go together in a whole bunch of different ways. Okay, so I have to say this is the trinitrogen dioxide versus this is the dinitrogen trioxide because they could go together any number of ways. That's why I need prefixes for molecular, why I don't need them for ionic. Okay, ionic can only go together one way so that those ratios hold and you do the swap and drop. Okay, or drop and swap, whichever way you're taught, it's the same thing. Okay, when you're doing the formulas. Okay, is that ringing a bell from last year? All right. All right, so for binary compounds, that means only containing 2 things. Okay, you name a binary compound by writing the name of the metal and then the name of the nonmetal and changing the name of the nonmetal's ending to "ide" or giving it an "ide" suffix. Okay, so like magnesium oxide, sodium fluoride, or aluminum sulfide. Okay. Everybody okay with that? All right, that's what we just talked about. So. Now, a couple of things. Always remember to name both parts. Sometimes people just forget one part. I don't know why, but it happens often enough that I bring it up. Okay, and here's the other thing. I still do this from time to time. This is a terrible habit because, you know, in English we're taught that names should be capitalized. Sodium chloride is not a name. It's a chemical designation. Okay, it's not like Jane Doe or John Smith. Okay, those would be proper names and would thus require capitalization. Sodium chloride is a chemical. Okay, we call it naming, but it's not really a name, so it shouldn't be capitalized. Okay, neither part. Now, would I mark it wrong if you capitalized it? No. But I'm telling you, it shouldn't be capitalized unless you're starting a sentence with it. Okay, sodium chloride tastes good on my fries. Yes, then you would capitalize the S. Okay, but otherwise, sodium chloride is not a proper name. Okay, nor are any other chemical names, so they shouldn't be capitalized. Okay. All right, things to remember here. Ionic compounds, or any real compounds, should have a net charge of 0. Okay, that means the positives and negatives have to balance. That's why you do the drop and swap when you're making formulas. Okay, it ensures that you have the same number of positive and negative charges and that it comes out to 0. Okay, now how do we know what the charge on everything is? Well, on lots of things, especially the metals, it's written in their boxes. Okay, so I would know that sodium has a charge of +1 and magnesium has a charge of +2. Okay, and that holds true for most of the metals. But when you get to the non-metals, they're not listed. Okay, so you're going to have to just remember this, right? The noble gases, far right, no charge. They're happy, their outer shell's already full. Okay, they're not going to get involved in anything. They have no charge whatsoever. Okay, everything in group 17 is -1. Everything in group 16 is -2. And everything in group 15 is -3. All right, now, I see a bunch of you writing that on your periodic table, which is fine for now. Just know that in Chem 20, those are things you have to memorize, okay? You have to just know that the noble gases, group 18, 0, group 17, everything's -1, group 16, everything's -2. It just comes across, right? Start at 0 and move to the left, and the number gets bigger, okay, for all the non-metals. Okay. What do we got for time here? 9:05. Okay, we're doing good. Okay, I want you guys to try a couple of these here. Let's see how we do. Let's try the first 4 there. Okay, so write those back. Don't have to do number 1 because we already did it. Okay, but let's try 2, 3, and 4. Write them down and give me the proper name for those 3. All right, let's have a look at number 2 here. So what does K stand for? Potassium. Okay. And it's with fluorine. Yeah, so we're going to have potassium fluoride. Okay? Everybody all right with that? All right, for number 3, is hydrogen a metal?
No.
Are you sure?
Yes.
What side of the periodic table is it on?
Well,
What's on the left side of the periodic table?
metals.
So why isn't hydrogen a metal?
Because on the periodic table, there's different colors for different metals and non-metals, and hydrogen is actually a non-metal.
Why? Why do you say that? Because it's blue?
Well, because it's blue, and if you go to the legend, it's a non-metallic solid.
Well, actually, it says it's a gas. Blue is for gas.
Oh yeah.
Right? Is
It's
it
a
possible
gas.
for a metal to be a gas? Sure it is. If I heat up any one of these metals enough, it'll melt, and then it'll boil, and it'll turn into a gas. Okay? It just so happens that hydrogen has an incredibly low boiling point. It is actually kind of both. It kind of behaves both ways. But it is actually incredibly metallic. Okay? It's why the sun has such an incredibly strong magnetic field. Okay? The sun is made up mostly of hydrogen. Okay? And there's so much of it there, and it's so metallic that it generates a gigantic magnetic field. Okay? So hydrogen actually is a metal if it's listed first in a compound. If I had hydrogen like this, then hydrogen would be behaving as a non-metal. Yeah. Okay, it'd be behaving as a non-metal. So hydrogen, because it only has 1 proton and 1 electron, can actually go both ways, right? To fill its outer shell, it could gain an electron and have that inner shell that only holds 2 electrons be full, or it could just lose the electron and have no shell at all, okay? Which actually it quite often does, right? So hydrogen can kind of go both ways as a metal or a non-metal, okay? If it's listed first, like it is here, it's behaving as a metal, and this is an ionic compound. Or if it's listed second, like it is here, then it's behaving as a non-metal, and that would be a molecular compound, and I would name it as such. So hydrogen's one of those ones we have to watch for, because it can kind of go both ways. Okay, so this stuff then would be hydrogen iodide. Okay, it's actually a very strong acid. Okay, ionic compounds that have hydrogen acting as a metal are typically strong acids. All right, number 4, what does Ca stand for? Calcium. Okay. All right, and Br?
Bromide.
Right, so calcium bromide. Do I need a prefix? No. It's an ionic compound, so I don't put a prefix on it. Okay, ringing a bell? Okay. Try those 4. All right, so looking at number 5, what does Al stand for? Aluminum. Okay. And I spell it that way. Okay. The International Union of Physics and Applied Chemistry says that it's actually supposed to be aluminium, which sounds awesome with an English accent, but terrible out of my mouth, and I can't do it. Okay. So this is going to be aluminum, and then what does At stand for? Astatine. So this would be aluminum astatide. Right. All right. Number 6. Okay. Cs stands for cesium. Okay. And what does S stand for?
Sulfur.
Sulfur. So this is going to be cesium sulfide. Right. Okay. And then number 7, we've got sodium, and it's with oxygen, so it's going to be sodium oxide. Again, no prefixes. That's the only way those can go together. All right, and then Ba stands for barium, and Se stands for selenide. So there's actually 2 ways you can write this. You can write it selenamide or selenide. Either one is fine. Okay, I like the short way. Okay, everybody good with those? Okay, let's try the rest of those there. Okay, so our first one here, Ra stands for radium. Okay, and Te is tellurium, so that could be probably telluride. Okay, so radium telluride for number 9. What would number 10 be? Lithium fluoride. Okay, number 11. Rubidium sulfide. Okay, number 12.
Strontium iodide.
Strontium iodide. Okay, 13.
Calcium oxide.
Calcium oxide. Okay, and 14.
Magnesium selenide.
Right, magnesium selenide or selenamide, either one. Okay. Well, let me ask you a theoretical question here. What would you call that?
Iron oxide.
Iron oxide? Okay. What would you call this?
Iron 2 oxide. No, iron 3 oxide.
Iron oxide.
Okay, we gotta have different names, right?
Iron
Okay.
3 oxide.
Yeah, actually, this one is iron
2
2 oxide. This one is
Iron
3. Okay, now if you're looking at it going, how do you know that? I'm going to tell you. Okay, but some of you have already learned that. That's great. Okay, some of our metals are called transition metals. Okay, and they are generally, or multivalent metals, they're also sometimes called. They're generally along the middle of the periodic table. So if you look at some of these elements here, you'll see more than one charge listed for them. Okay? Any ones that have more than one charge lose different numbers of electrons. Okay? Sometimes iron gives up 2 electrons. Sometimes iron gives up 3 electrons. There's 2 different kinds of iron. Okay? The kind of iron that has 2+ charge and the kind of iron that has a 3+ charge. Right? Now, they are not equally distributed. Okay? Most of the time, the first charge, so like for iron, 90 or more % of iron is going to be the 3+ variety. Very little iron is going to be the 2+ variety. Okay? But we still have to have a way to name these 2 compounds differently. Because if we just follow the regular ionic naming rules, they're both iron oxide. And that could be a problem. One of them could be an important mineral for your body, and the other could be highly poisonous. That's not the case, but let's just say theoretically, okay, that could be a thing, and that would be bad. You wouldn't want to write a paper about the health benefits of iron oxide and have it be the wrong one and people die. Okay, so you have to have a way to tell these apart. Okay, I mean, it's just like in here, right? Everybody's got a different name, so I can tell you apart, except for the one class I had where I had 2 Chase William Andersons. First, middle, and last name the same. And they could not have been more different, okay, in terms of the people they were, okay, but they had the same name. I'm sure I messed up something along the way, okay, in marking that paper. Well, probably not, because they were very different people. But, okay, the point is, it's very difficult when 2 things that are very different have the same name, okay, and chemistry recognizes that. So, what do? Well, we actually put in a Roman numeral into the name so that we can tell. This, if we're writing a sentence where we don't write the formula, someone knows, oh, that's this iron oxide versus this. So here's what we do. The Roman numeral that we put in the name tells us the charge on the iron that was involved. Okay, so as we said, both of these would be called iron oxide. That's a problem. Okay, so I've got to be able to put in a Roman numeral that tells me which iron it is. So here's how I tell. Does oxygen have more than one possible charge?
No.
No, it's always -2. All right, so if I ever have an ionic compound and it involves one of these metals that has more than one charge, I use the non-metal to figure out what the metal's charge will be. All right, so oxygen is always -2. There's 1 oxygen and there's 1 iron. This compound has to have a net charge of what?
0.
Okay, so what does the charge on iron have to be then?
+2.
+2. Okay, all right, so I figured it out. This is the iron with the +2 charge. So this is iron, Roman numeral 2, oxide. Okay, do I need to put that in there if the metal doesn't have more than one possible charge?
No.
No. I only use it for metals that have more than one possible charge. Okay, now the same is true here. Oxygen always has a charge of -2. How many oxygens do I have?
3.
Okay, so how many negative charges do I have?
6.
Okay, so that means I've got to get 6 positives from how many irons?
2.
What's 6 divided by 2? 3. Okay, so do you have to do a little tiny bit of math? Yeah, a little bit of multiplying, dividing, okay? So it's not like terribly, it's not rocket science. Okay.
Wait, what do the Roman numerals look like? It's hard to see from over here.
Okay, so the Roman numerals, 1. They're in brackets, that's why they look weird. Okay, so 2, 3, 4. This is part of the reason the Roman Empire fell. Their numbers are silly. Okay, you won't have to go past 5 for our purposes, but yeah, it's I is 1, B is 5. Okay,
X is 10.
have a good weekend. but not too good. Okay, don't forget your phones on the way out, guys.